Good afternoon, everyone. This is Lee, and I'm from Sogang University in South Korea. Talk of, Title of my talk is quality factor and vibration amplitude-based viscosity measurement using suspended channel microresonators. This is our outline of my presentation. I will start brief introduction, and next I will introduce suspended microchannel resonators. And then next I show you experiment and resultant discussion. Viscosity is a measure of Viscosity is a measure of fluid resistance to flow and one of the most fundamental properties of fluid. Viscosity is expressed this equation, this relation between shear stress and velocity gradient. Viscosity is very important in many industrial areas and in ink or painting industry. Viscosity of ink and paint affects painting and printing quality and many other viscosity and some lubricant and healthcare and food industry and cosmetic industry is also important viscosity. Many different type of viscometer is developed. The principle of viscosity measurement is applying shearing motion and measure flow resistance by means of pressure, time, or other physical measurements. Many different types of viscosity is this. Capillary tube and folding ball type measure time, and rotating cylinder and rotating cone type measure torque, and vibrational pedal type measure damping. In general, conventional viscometer require 10 milliliter or more samples, so it is not suitable rare or expensive samples. But to solve this issue, many MEMS viscometer is developed. This four examples of micro-resonator viscometers. This four types achieve to these very small sample, but this four resonator type viscometer is operating in liquid, so this device has very low quality factor. Most viscometers mostly rely on measuring the quality factor. Definition of quality factor is ratio of stored energy to displaced energy per cycle. Micro-resonators operating in liquid. This has a very low quality factor due to viscous damping and inertial loading, and this is why its resolution is micro-resonator is in liquid are limited. In contrast, operating in vacuum, this device has a very high quality factor because this don't has medium, so very high Q. Then how to measure fluid viscosity in vacuum? A promising solution is used to use the suspended microchannel resonators. SMR is new class of microfluidic MEMS device. Resonating structure of this device includes embedded channel, and this is a vacuum package for quality factor enhancement, and this device has resolution is femtogram resolution, ideal for mass sensing in wet environment. Since these devices include embedded microfluidic channels, so SMR can be used for measuring properties of liquids such as viscosity. Two methods are developed for viscous measurement. The first method is open-loop Q-factor measurement, and second is closed-loop amplitude measurement. Q-factor measurement has more precision than amplitude-based measurement, and in contrast, amplitude measurement is more faster than this method. In general, these are three representative ways to extract quality vector: frequency, and ring down, and sum noise. Among them, frequency method has smaller random error than other methods, so frequency is selected in this work. Before do this work, relation between quality factor and viscosity in SMR is studied by Professor Sader. Quality factor is function of viscosity. In typical cantilevers, Q-factor of typical cantilevers is decreased with increasing viscosity, but SMR is not monotonic trend. The reason low viscosity range, this figure is cross section of channel. In low range of viscosity, boundary layer is very thin, so this layer is thicker and thicker with increasing viscosity, so damping is larger and larger. So quality factor is lower and lower with increasing viscosity, and in high viscosity range, boundary layer is too thick, so two boundary layers is combined one. So the behavior of this some rigid body. So quality factor is larger and larger with increasing viscosity. This is a custom optical level setup. Laser is extended by beam expander and split it, focused on SMR, and reflected beam is focused on photo detect. This is a picture of my setup. Before doing main experiment, we check vibration mode effect. Three vibration mode is checked for finding the most sensitive mode. First mode is best suited for low range viscosity measurement. The plot on the left shows viscosity depending on temperature. This axis is viscosity, and this axis is glycerol mixture. We check three other temperature. Low temperature is high viscosity, and viscosity is lower and lower, and with increasing temperature. This is a calibrated data each temperature. Also, x-axis is glycerol-water weight percent, and y-axis is quality factor. Quality factor is depending both temperature and viscosity, so SMR should be calibrated at each temperature. The plot shows the result of viscosity measurement by Q-factor based method. In previous slide, I mentioned the Q-factor has a local minimum. However, the result of our experiment is monotonic increase in our intensity viscosity range. Since Q-factor of this SMR has local minimum is lower than 1 millipascal per sec. So Q-factor exhibits some bilinear behavior. In this region, resolution is 0.035 millipascal second, and this region resolution is 0.156 millipascal second. This experiment is doing at 20 Celsius. This slide shows result of viscosity measurement by amplitude-based method. Delta amplitude exhibit bilinear behavior. Likely to Q-factor method is two reasons. So resolution is lower than Q-factor based method, but this method is more faster and faster measurement than Q-factor based method. And two results is well matched. So we think this device is these two methods is suitable for viscosity measurement. For measurement validation, we cross-check SMR and commercial tuning fork viscometer. At first, we choose two samples, heavy water and 9.65 weight percent glycerol-water mixture. This is a static viscosity of two samples and different two sample viscosity, but after then density correction and viscosity of two samples is well matched. And next we measure two samples by SMR. Q-factor is almost same. Comparing between SMR and tuning fork viscometer, SMR need only 10 microliter sample volume, but commercial tuning fork viscometer need 10 milliliter samples. Each operating frequency of SMR and commercial fork viscometer is 19 kilohertz and 30 kilohertz. Measurement of SMR is density and dynamic viscosity independently, but tuning fork viscometer measure static viscosity. So SMR don't need density correction, but tuning fork require density correction. In conclusion, Q-factor based and amplitude based method are developed for viscosity sensing, and two methods provide equivalent result, and select method depending on requirement. Need precision, we select Q-factor based method, and we need fast sampling and we choose amplitude based method. In conclusion, SMR is well suited for low range viscosity measurement. Acknowledgement. This work supported by National Research Foundation grant funded by Korean government, and thanks for nanoscale sensing laboratory members, and also thank Professor Scott Manalis at MIT and Professor Thomas Well and Max Planck Institute. Thank you.
Thank you. Now is the open for questions. Any questions?
Yes. To figure. This figure is a cross-section area in SMR. Boundary layer is thicker in lower viscosity, and boundary layer is thicker and thicker with increasing viscosity. So fluid resistance is larger. So damping is larger. So Q-factor is lower. And in this viscosity range, thickness of boundary layer is more than half of height and width. So combined one rigid body, this behavior is some rigid body. So viscosity is larger and larger. Some rigid body is some harder and harder. So Q-factor is higher and higher.
Any other questions? Actually, I do have this question. What is the temperature point? Is that just the moment your liquid totally fill with the channel? And that's the temperature point.
This point?
Yeah, that's okay. And just totally fill with the channel.
Exactly. Combined one is not this point. Actual some little this.
So even you don't refill totally your channel, your Q will go up at some point.
Yes.
Any questions?
Yes. We use pressure drop for injection sample. So and we after measurement and we first so first loading water and so flush and whole thing and ethanol something solvent and we wash and so pressure. Yes, but interest range is our interest range is very low viscous range. So few minutes they take it in few minutes.
Okay, thanks Peter again.